Well, it's great to see so many of you back from yesterday. Yesterday was, quite an event with a formal dedication of the building that you've all seen. I mean, the beautiful new space that is, I think, going to transform our department for many years to come. Yesterday, of course, was, it was a lot of formalities. Today, it feels like more family event. I mean, I see many, of course, well-known faces and alumni, and I'm really happy that many of you found a way back to the Green Building. So today we have a packed agenda. There's many things that we are going to do that brings back alumni, people that have worked here for a long time, and hopefully give you a very nice overview of the department. But mostly, I think we're all here to reconnect to one another and have fun. So after all, this should be a celebration of the 40th anniversary. The 40th anniversary, as you well know, was actually last year, 1983 to 2023. But we really wanted to do it, in this new space. And this new space came along in a long time because of COVID, supply chains, labor issues, what have you. I'm not going to spend the next 10 minutes to complain about those things. But here we are. We got the certificate for occupancy only a couple of weeks ago, and so we kept postponing this particular event. But here we are, and I'm really delighted to have you here. So what I would like to do in the next 15 or 20 minutes is to reflect back a little bit on many of the things that have changed. I see many of you, of course, here are current members of the department, so many of you will know part of what I will say, but there's also many people that haven't been here for a long time and might be interested to see how things have changed indeed. So this is, 4 decades of discovery and education. That's what we will emphasize today. EAPS is a vibrant home for multidisciplinary, curiosity-driven research to understand processes shaping the natural world. That all brings us together, and we do it in very different ways. But let me start with a brief history. Those of you who were here yesterday have seen this, but it is also good to remind us, how we got here. And we got here already after a very long journey, in particularly for geology, starting with the very opening of MIT in 1861. William Barton Rogers, as you all know, was a geologist, and he was the founding president. And ever since that day, there was a course geology. The course number was different, but that course number changed to 12 in 1890. And a year later, the first student who got a degree from course 12, from geology, was Dixie Lee Bryant. And I'm very proud to say that this space, which of course is always known as 54100, and where we always have the GIR lectures, many of the undergrads of MIT come here, will be formally named after her, the Dixie Lee Bryant Lecture Hall. Then fast forward, 60 years ago, we had the Green Building was being dedicated, so exactly 60 years ago, and now of course we just opened yesterday the Morgadam building, Tina and Hamid Morgadam, that you all have seen downstairs. There's also a rich history, of course, in the counterpart that merged in 1983, that was course 19, and that was meteorology and physical oceanography. Meteorology started in the late 1920s with Rosby, actually in a different department in Aeroastro, and then later it changed course numbers all the way to 19, and then course 19 was meteorology and physical oceanography merged with earth and planetary sciences to form EAPS in the way we know it today. There were some really small changes, well, significant changes, but small in the big picture later, but I'm not going to talk about this. You also see, of course, many of the famous names that you're all familiar with, from the Charney Library to the Houghton Lecture and Schrock Professorship and all these things. And they were actually real people, of course, and they really were pivotal for the history of our department. In the 50 or the 40 years since we merged, there have been 5 department heads, and I think we should all thank them, because then they really were very helpful and instrumental for getting us here. Bill Brace was really the person who put the two departments together, probably not from his free will, because it was the provost dictated like, okay, we have to merge. And Bill, I think, did a remarkable job, building the community across those two departments. He introduced, for example, the Thursday faculty hours that we still have, and that really brings our faculty community together. And we have later in the program, we have people that were there at that time, and they can speak to that era. Then Tom Jordan took over for 10 years before he handed the baton to Ron Prin. Ron is here, Maria Zuber is here, and then I took over some 12 years ago. So in that time, many things have changed. And what hasn't changed is the technology to forward slides, and I make the mistake of pressing 5, so it all goes. Could you advance the slide, please? Right. For those of you who know me, you may be surprised by this slide because I really don't care much about rankings, because they're very flawed in many different ways, but still they tell a story. And many things have changed over the past decades. And I think that change is absolutely fantastic, and we will talk about some of these things in the next 15 minutes, but also the rest of the day. But quality and excellence have not. And one way to express that is to look at the rankings over the last 30 years. I couldn't get the earlier ones. And rankings are, very difficult because what does earth sciences actually mean these days? I mean, many departments have different compositions of earth sciences. Many of these rankings change over time quite a bit. If you look at what's happening to Berkeley, Stanford and below, there's actually a wild change of positions. But what has been remarkably stable is the numbers 1 and 2 with Caltech and MIT. And I'm looking at John Grossinger here to say, hey, welcome back, our friend. And so MIT has been doing very well over the years. Because despite all these flaws of the rankings, they do signal that over the decades, our department has consistently been perceived as a top department, with emphasis on perceived because it is kind of a subjective measure. And on a day like this, it is kind of interesting to ponder and to pause and say, what contributes to this? What creates this stability of quality? And I use these rankings in a way to kind of structure the rest of my presentation to look at a few elements of EAPS, what makes EAPS such a fantastic place. And of course, it starts with the quality of the people. Top faculty and researchers, they attract top students and postdocs, and vice versa. And it's really the quality of the students that really attract many of the faculty here. And that is really a fantastic kind of dynamical system that we should really keep. And that's always what we often talk about strategy, but really keeping this dynamics strong is basically the best strategy that we have. What is also very important to EAPS is that we have a very exciting, curiosity-driven and diverse research program. And it's increasingly connected to societal impact. It's, I think, the diversity of our program that is very attractive and that we really cross these different fields so beautifully, and I will talk about it a bit later. We have world-class facilities, laboratories, and analytical facilities that didn't always used to be the case, but we've worked hard over the last decades to improve that. It's of course an integral part of MIT's open research environment, and it's contagious and drive to innovate and make a difference. And it's that connection with MIT that we should not underestimate. I mean, it's really a fantastic petri dish of innovation here, and more we make use of that by connecting across campus to our friends. The MIT Woods Hole joint program, I think, is a real gem for us. I mean, it's been very important for over 50 years now, and that is something that we continue to strengthen over time. But of course, the fantastic community is really what makes us, and that is something that we've all worked on very hard over the years, and I've worked very hard on over the years. And even the building that you see, I think, is primarily a mechanism to improve community rather than just adding a classroom. It is really going to transform how we work together here. The community has been kind of stable over the many decades since the merger. We roughly have about 400 students, staff, and faculty. And of course, we have many, many more alumni, and many of the alumni are here, and to see what has happened over the last 40 years. And I think it's great that you are here. Together we can do amazing things, and to do these things we really have to work together. And it's not just, you know, the faculty that stand out, as I mentioned, it's the synergy with the students, but it's also the researchers and also the administrative and the support staff. Everybody has to be top of their game in order to make the whole as strong as it is. And that's what we need to continue to do. Times have changed the student numbers, but actually not so much. I mean, if you look at this graph, the orange bars are, you know, since 1994, so the last 3 decades, the change of the graduate numbers, and it kind of fluctuates, but it always hovers around, say, 170 or so. About 45% of that is women, and also that fraction hasn't really changed over the decades. And the lower bars, the dark blue bars, are the undergraduates. As you know, it's much, much smaller. We have always been a very small undergraduate department, despite our efforts to increase those numbers. Those numbers are very stubbornly low. We hope that that will change. But in the meantime, we have also made great efforts to connect to the MIT undergrads in different ways. For example, for those of you who are here, we have the Terrascope program directed by David McGee, who connects every year to about, say, 50 or 60 undergrads at MIT, the freshmen. And we have the experimental studies group led by Vicky Royden. There's another one of those early learning facilities at MIT that's also led by MIT, so by EAPS. And so beyond these small numbers, we actually do much more to connect to the undergrads. And over the years, we have you know, awarded some 900 degrees of various types, and that's an amazing number. And as I said, many of you are here. That is also that base of alumni, of friends, for all the support that we have received over the years has been incredibly important. Faculty demographics have changed quite a bit as well. I didn't get a picture from 1983 at that particular moment, and I didn't have a picture of the counterpart, course 19. But this kind of is representative that, in the 70s, the demographics was, of course, very different from what it is today. They're all white men, which is not the case anymore. But some of the people in the picture you may recognize, and some of them actually are here. The tall guy on the right, third from right, John. You see yourself. And John will join us in conversations about that time a little bit later. Carl was here yesterday. Is Carl here today? Carl Wunsch is in the picture. And of course Navi Toxos. They've been here for a long time. But of course that has changed. It started with 100% gender imbalance, I would say. And over the years we have really changed that quite a bit. It's a slow process, but right now in 2024 we are certainly not at parity, but we have about 34, say a third of our faculty, in particular young faculty, is women. They did a study a couple of years ago, actually, our students from EAPS, and they looked at these numbers, and on the one hand you can say this is tremendous progress. On the other hand you can say, well, if it took us 30 years to get to these kind of ratios, I mean, it's still very slow, and that is true. And that is not unique to EAPS. I mean, that is true for earth sciences in general. So let me now switch gears and give a very, very brief overview of the type of research that we do. As I mentioned, it's an exciting, curiosity-driven and diverse research portfolio that we are very proud of. And much of what we do can be captured in the 4 themes that I mentioned here: Earth, planets, climate, and life. For those of you who were here, especially a little bit earlier, like in the 90s and in the 2000s, there was all talk about research and disciplinary groups. And there's PAOC, and there's PGGG, there's PG, Planetary Sciences. most of the time we don't really talk about it so much anymore, and in terms of the presentation of our research, we like these themes because it connects much better to the outside world. And it also connects, I think, much better to what we try to achieve internally, is kind of cross-cutting through these programs. So the way we see it now is we have these 4 programs as kind of the columns of our system, and the themes that we have, they really cut across them. Programs are still very important for education and to set the curriculum. I mean, we need to have that domain expertise, of course, to do that. But the themes are really becoming much more important in terms of the research and the integration across these programs. Earth, of course, I can spend the next half hour and talk about all the beautiful things we do in this particular theme. We do a lot of field work, of course, all over the place. We look at volcanoes, and I've been following in the last week, or the last month actually, what's happening in Reykjanes Peninsula, of course, in Iceland, with the repeated eruptions there. This is not a picture from there. We go all over the place. I mean, the group below is from Svalbard. You know, we like to visit places, and it's also connecting to, of course, people living on Earth in the lower right. It connects to the energy, it connects to the energy transition in terms of, you know, the minerals, for example, how that connects to climate change and the transition that we have to face. Planets have become much more important over the last decades, you know, thanks to many aspects. I mean, people, of course, here, but also the opportunities. There's so many missions going to distant places in the universe, and in many of them we are really part of it. So we are relatively small, but I think, you know, for that small, I think we are really punching above our weight in terms of the planets. And of course, we use our knowledge about the Earth, you know, to interpret what we see in other planets. Climate, of course, is growing, not only in importance, but also in terms of, you know, what it does in our department. And many people, not only connected to the traditional PAOC group, but many other people are connected to climate in different ways. Life is something that, if you haven't been here for the last 20 or so years, that may be new to you, but with the arrival of Roger Summons, you know, in the late 90s, we really started a very powerful and world-class geobiology program. And I think by now, depending how you define it, a very, very large fraction of our faculty is somehow connected to the effects of life even on geology, but also the co-evolution of life with the environmental systems and our planet itself. What also has changed is how we work. We really, as I mentioned earlier, we are an integral part of MIT, and we have a lot to benefit from that. And so we really connect very well, and increasingly so, with our colleagues across campus. Our partner in crime, in particular in environment and climate, is Civil and Environmental Engineering, CEE. We do a lot together. We have common events, and we have, you know, joint appointments that we make, and we share our knowledge in terms of faculty searches. We have even started a new course, the course 112 in Climate System Science and Engineering, that started last year, and as far as I know, that is going very well. So those cross connections are very important, also to leverage our science for better solutions. And I highlighted a few here: the Environmental Solutions Initiative, who will be partners here. They will also be co-located in our new space. Terrascope, I already mentioned, and Woods Hole. What also has changed over time is where we work. Many of you remember in the very early days that we started basically in 2 main units. We had a few other places across campus as well. But of course we started in the Green Building in 1964. And ERL. I didn't have a good picture of ERL. We didn't work there in this current state on the picture. This was later, when it was in the process of being demolished. But NAVI and the Earth Resources Lab, I mean, they moved to Carlton Street, to ERL at that time. Then sometime later, you know, then Roger Summons came. There was the beginning of, 3 minutes remaining, I will go quick. The beginning of geobiology moved to E25. ERL since then occupied the space that was formerly the Lindgren Library. There's many people that, of course, contributed to the leadership of ERL over time. Then a couple of years ago, we opened the Rasmussen Climate Lab in Building 4, one of the main group. And of course, just now we opened the Moghadam building. And in the building, what you have seen is not just a beautiful building, but there's also a lot of artwork that I hope you have some chance to look at. I think it really beautifies the space, and it's artwork by Julien Charrière and Katie Patterson. Just above the picture on the lower left, there's a big number, and that's actually the counter of sunrises since the beginning of Earth. Don't ask me when they started and how they did that. You can actually read about that. But if you come here tomorrow morning at about 7:30, you will see that that number will change. And of course, the building itself has changed. Many of you, remember the very, very bad situations, from parking lots to rusted pipes to flooding. And we have complained bitterly about that. We have sent many pictures of, like Paula here, freezing in my office. And finally, they gave us permission to do something about that. So over the years, what has happened, not just to see the change in space that you saw downstairs and also this beautiful lecture hall, but many things have been done. New restrooms, water, rooftop, new elevators. Actually, they work most of the time. So there's a lot of things that happened over the years. What also has changed is the way we actually finance our business. Fundraising has become very important. We could not rely anymore on federal funding only, or on the gratitude of and the grace of the MIT Institute. You can do many things. I think you can do everything you want to do here at MIT, as long as you find the money to do it. And that is what really has changed the business, and we've been doing that quite successfully over the past decade in particular. What also has changed is how we care for one another. And that is very important, of course, to keep the department strong for the decades to come. We pay much more attention to things like mentoring, both students, but also our junior faculty when they come in. We have all sorts of events to bring the community together, but also to share, knowledge about, how do we do things. And then we have yearly quality of life surveys. By the way, for the current members of the community, if you haven't filled out your forms yet, you still have a few days to do that. So with that, I will end. My time has expired. And I would say happy birthday, EAPS. I think it's a fantastic department, has always been, and it's, I think, getting even better. With the people, with the space, with the community that we are building, and with all of you here. And we will hear many more stories about that in the course of the day. So thank you very much, and have a fun day. And now I hand it over to the MC for the day, David McGee.
Thanks, Rob. It's good to see you all here. I'm really excited about today. We're going to have 2 sessions before lunch and then several sessions after lunch. And they roughly fall, the first session looks at the present in EAPS, what's going on in research across the department right now. Then the second session before lunch and the first session after lunch look back, look at the ripple effects of people's time in EAPS in their own careers and throughout the world. And at the evolution of the department over the last several decades. And then after that, we look out and forward. First, out literally, looking at work in planetary science and on exoplanets. And then out in a kind of figurative sense, looking at our work in interdisciplinary spaces through the climate grand challenges. And then finally, we end by looking forward with a panel of mostly junior faculty and graduate students. And then after that, there is a reception that we'll say more about in the afternoon. So our first session, we're going to have 4 faculty from EAPS, the chairs of the 4 disciplinary programs. Tom Herring, the chair of the program in geophysics. Ali Jagoutz, the chair of the program in geology, geochemistry, and geobiology. Susan Solomon, the chair of the program in atmospheres, oceans, and climate, and Ben Weiss, the chair of the program in planetary science. So they'll come up in that order. Each will give about a 6 or 7 minute summary of what's going on in that disciplinary group right now in EAPS. And then after they're all done, we'll invite the four of them up here and have a short time of Q&A. So first, Tom.
Thank you, David. That's noisy. Thank you, David. It gives me great pleasure to, if I go to the, yep, perfect. The program in geophysics is one where we seek at the moment to understand the deformation of the Earth and how it interacts with tectonic forces and the fluid envelope that is around our planet. And we do that through a series of field measurements, laboratory measurements, and system modeling with elaborate computer programs. And you can see the faculty that are involved in the geophysics program as their primary affiliation on the right-hand side of the figure. And today I'm just going to highlight a couple of issues. First is ice sheets and their dynamics with sea level rise, what we're learning about earthquake physics, and what we learn about deformation processes in general in the planet. So ice sheets is led by our glaciology group and remote sensing group, which is led by Brent Minshew, but also has a large number of undergraduates and graduate students who work in that group, plus research scientists and postdocs. And the real questions being asked is how quickly will sea level rise in the next 75 years? And what can we do to help mitigate that? And to sort of think about ways that we can actually stop some of that sea level rise potentially. And much of our uncertainty about how sea level will rise is driven by actually a very small part of Antarctica, the West Antarctic ice sheet. And the figure on the right over here, the colors inside Antarctica, that's how fast the ice is actually moving. And the scale here, you'll see it's 3 kilometers per year in places. Now, some of this ice is floating, and much of it is actually sitting on solid Earth. So as that ice melts, the solid Earth rebounds from that, and we can study the processes through that. And that's what this team does. It looks at deformation measurements, develops theories on how ice fractures and how it moves, and it involves most of the actual elements of solid Earth geophysics, but because it's ice, it actually happens much faster. You can really grind those PhDs out at a rapid pace. Now, speaking of things breaking, we also have our work on fundamental physics of earthquakes. And this is led by Camilla Catania, who is one of our junior faculty members, and her group again. And the idea here is to look at why some earthquakes have sequences that occur before them, called foreshocks, which unfortunately we don't know are foreshocks until the main shock occurs at the moment. And that's the fundamental question we're trying to address. And the real question is what leads to the development of these large earthquakes? The figure on the right-hand side shows a mathematical simulation of time going up the axis and then along a fault. And you can see these small little ruptures, those are our foreshocks, and they eventually build to that large main shock. Now, one of the interesting things coming out of this research, it's computationally very intensive to do these calculations realistically, but the simple friction laws that are used can show very complex behaviors. And what is involved is the complexity of the fault structures on which these events are occurring. This is the type of work that Camilla and her group are looking at. Now, we also see different types of earthquakes, and this is which is work being done by William Frank and his group. And again, the question becomes, what causes swarms of earthquakes to occur? This is a phenomena in which you have tiny, tiny little earthquakes, and in some cases, those just go on and then they just peter out and go away. In other cases, they actually lead to a major earthquake happening. And currently, we don't understand what that interaction actually is. And William and his group have been investigating a particular event, and they're looking at the velocity changes that are occurring. And the figure here is reservoir type modeling, which goes with our Earth Resources Lab. The little blue line is the pore pressure being calculated at depth below where these earthquakes are occurring. And again, that is leading us to realize that as the pore pressure increases, you tend to see an increase in this swarm behavior. And understanding the nuances of that, and it brings us to the fluids being involved in the work that is being done inside of the Earth with these mechanical processes. Now, of course, you can't do everything out in the field, and that's where we go into Marte's work in his lab, Mate Peck's work, and his group looking at laboratory measurements, where essentially we're again looking at different levels of pressure. We can look at the actual rock being deformed, the microstructure that's involved, and then importantly, the acoustic emissions that are coming off, because that's how we're going to actually see this in the real world. And what Marte's looking at is this transition between the strength of brittle failure at depth, which leads to earthquakes, and sort of constant flow at greater depths, which is the driving force essentially behind plate tectonics that we observe. And it's the area in the middle, that brittle transition, brittle ductile transition that Mate and his group are studying in the lab. But that also occurs in something we can observe in the field. And these are earthquakes, which I would just say are on a different time scale. And again, William Frank works on this a great deal with the types of seismic measurements he makes. And this is where we're looking at this sublized through a subduction zone. So you have earthquakes here, this is the brittle part. You have flow down here, but in the middle, this phenomena of what are called slow slip events is occurring. They occur and have been well seen in the subduction zones, primarily because the area over which they occur in a depth range. In the subduction zone, that's a large area, so we can see something on the surface. And that's what we do with GNSS stations on the surface. And you see a time evolution here where what appears to be an earthquake, but instead of taking tens of seconds to happen and radiating high frequency energy, it occurs over a period of days, sometimes months, particularly in this area, several months. And untangling that and how stress is moving and changing things on the interface, that's the fundamental questions that are being addressed. So in highlights of the geophysics program at the moment, we've sort of shown that we deal with ice sheets and impacts of sea level rise, fundamental processes associated with earthquakes, both computationally being modeled, being studied in the lab, and looking at their consequences with field work on the outside. And we see these types of earthquakes and deformation processes that are occurring that reveal that we have rapid earthquakes, but also slow earthquakes. Now, you will see the geophysics faculty appearing in these other talks, as Rob had mentioned. We work across disciplines, and we are going next to the geology, geochemistry, and geobiology, where you'll see some of these faces again, and that will be Ollie Jagoutz.
All right, whoa. Okay, sorry, I can't do it this statically. Anyhow, thanks so much. It's a great pleasure to present the group in geology, geochemistry, and geobiology, and we all tangle up when we say it, so we just call it G-Cube. But I want to point out that the wrong way, how surprising, that the ancestral member of our community is, of course, Roger William Barton, and if you look at the course catalog of 1865, you will see that geology was an institute requirement for every second year MIT student, so was German. So as a German-speaking geologist, I feel very much at home here. And what you see by the infectious smile that we all display, that we are clearly the fun group in this here. Anyhow, so we are a very interdisciplinary group, okay? Many of us have co-listings with others. I just want to point out a few changes in personalities that we had over the last years. So last year we celebrated the retirement of Tim Grove and Roger Summons, but we also hired 3 new faculty members, that is Gaia, Nicole, and Lyle that joined us, and Lyle will join us by July this year. And then it's sad to say that our longtime friend and member, Clark Birchfield, peacefully passed away surrounded by his family a couple of weeks ago. And Clark was very much instrumental in starting the field program that is a core of G-Cube. And when you go in the field, finding a bathroom spot can be a little challenging, but clearly Clark mastered that. And I'm glad to say that the field program that Clark started still continues until today. So we just had an excursion which was sponsored by the department to go to Sicily. We took 20-something students there. And we just came back from the field camp that happens during IAP in the Mojave that was started by Clark. And Clark himself was a faculty member here for 39 years, so nearly as long as the celebration that we do here today. And so what we do in G-Cube, so we have these 4 bubbles. This is a talk of lots of bubbles, I guess. So we take field observations, we take laboratory experiments, geochemical data, and quantitative models to address these questions. So tectonics, magmatism, climate erosion. The tectonic climate connection was already part of the research portfolio when these two departments merged. As Rob said, we added the component of geobiology some 20-something years ago. These people think about the origin of life, coevolution of life and the environment, and the carbon cycles, things like this. And then the last thing that we sort of started to add to our program in the last 3 to 5 years or so is things that are societal relevant, like carbon sequestration, energy, critical minerals, and preservation of the environment. And I do this presentation a little differently. I want to highlight 3 students' papers that came out of this because, you know, the main thing that that we have here is excellent students, and they do excellent works. And so I highlight 3 different papers here. The first one from Maya Stokes, who defended her PhD in 2021. She's now at Florida State University. And she studied the distribution of this tiny little fishy here, and that fishy here loves metamorphic rocks and doesn't like sedimentary rocks. So it has a real place in my heart. You know, it's the metamorphic petrologist of the animal kingdom. And its distribution is shown as these white dots here. And as you can see, for some of these river catchments, the branching points is within the sedimentary rocks that the fish doesn't like. The fish likes these blue-rich rocks here. And what they show in this paper is that the distribution of this fish here is inherited from a structure that is older and eroded away. And they show that erosion, these metamorphic rocks originally overlay these sedimentary rocks here, and the fish could move around. And then erosion eroded those metamorphic rocks away here. And so now it has this restricted habitat. And that forces the fish to diversify. So that shows how diversification and geological process go hand in hand. The second paper I want to highlight is by Sam Goldman, also PhD 21, also at the University of Miami. I don't quite sure what it is with the COVID kids in Florida, but I'm sure Ron DeSantis will tweet about it if he picks it up. But what Sam did, he took the challenging task to look at ancient rocks. So here at this slide, you see these are 500 million years to 440 million years. And he tries to reconstruct the temperature of the ocean these rocks precipitated out. Okay, and that's a very challenging task because these rocks are old, they undergo a lot of processes, they have a long history, and you try to look through all these processes and see their original signature. But in this proof of concept study, Sam did very well, and he could show that the temperature variation that he reconstructs here with the help of clumped isotopes coincides with things like increased diversity, okay? And it's this correlation between the evolution and temperature that lets us better understand what we are going to do to the environment if we continue with this climate experiment that we are doing. And that leads me to the last paper that I want to highlight by a student, Josh Murray, that is still with us here. And what Josh did, Josh looked what are the weathering products of different rock types. So if you have what we call a felsic rock, you should think about Sierra Nevada granites. You know, when you go to Yosemite, El Cap, when it weathers, it forms a certain clay mineral. And when you think about Hawaii, basaltic rocks, when it weathers, it forms a different clay minerals. And these clay minerals make a huge difference the way we can sequester organic carbon into the rock record, okay? And studies like these, I think, are influential because they show us how nature sequesters carbons. And if we understand how nature sequesters carbons, then we have a chance to maybe engineer some of these processes and find a solution for the anthropogenic climate change. And that leads me to my last slide here. I got it, 1 minute. So the newest thing that we're adding to our portfolio is you know, what I said, that we are trying to understand natural process in the hope that it helps us with some of the problems that we are facing. So, no, sorry, it didn't work. So we have the Advanced Carbonated Mineral Initiative that includes a lot of people from biology, chemistry, and the Earth Science Department here. And they're pictured here, where we try to understand natural processes that we hopefully can engineer in carbon mineralization. There are posters in the hallway from postdocs and students. You should go and ask them lots of questions. And the last thing we add currently is whether or not we can use natural processes to produce geological hydrogen, which could help us with the energy transition. And with that, I'm supposed to hand it off to Susan, who I don't see. There she is. Thank you.
shirt. I'm just amazed. I get the chance to talk about PAYAC, which is the largest, I think, of the branches of EAPS. And I would just want to emphasize it's made up of a very large group of enthusiastic faculty, postdocs, research scientists, and students of all kinds. We do basically a mix of things, and so I'm going to show you one more little bubble diagram. Biogeochemistry, some of which touches on what Ali just talked about. Atmospheric chemistry, atmospheric dynamics, and physical oceanography. And I have to make sure I get this right. Yep. So I'm just going to go through a few of the many really fun studies that we've done in the last few years. You'll hear more about PAYAC, much more this afternoon when we talk about the climate grant challenges. Of course, climate is a huge emphasis in PAYAC, and many of us are involved in that new enterprise, the grand challenges. I'm going to talk about some of the other things that we do, and I couldn't help but show this one because not only is he smiling, but Raf is actually on a gondola in that picture, very appropriate. But it's such a wonderful study. I first want to start you out in the deep ocean. And Raf and his colleagues actually produced a tremendous paradigm shift in how we think about transport in the deep ocean in the last few years. So the textbook picture has been that waters rise very slowly from the abyss. You know, the abyss. They make movies about this. But Raf instead has this little movie where he's showing you that they're not rising at a rate of meters per year, but instead they're actually rising remarkably fast along ridges and seamounts at speeds so much greater, 100 times greater than what we thought. So it really was a huge paradigm shift. He did it first with geophysical modeling, geophysical fluid dynamics modeling, and then actually released a tracer on the bottom of the ocean and did this experiment. But don't worry, no sharks were harmed in the course of this work. And I really want to give a shout out to Ed Boyle. Ed led the Woods Hole Joint Program Group for a long time. He's one of the tremendous leaders in the world in studying lead. He's done that for many, many years. And one of the studies that he did recently with his group involved looking at the particulate veils in the North Pacific that are actually capable of scavenging lead. So lead goes into these little particles, which are things that look like this. So they're mineralized carbon, and they carry the lead all the way down to the abyss, down to that region that Raf was studying. And it's important because this lead, the isotope signature of it, tells you something about its origin from coal burning in different places. So Ed's been doing great work on lead for many, many years. I also want to now come up for air and talk a little bit about atmospheric chemistry and highlight the fact that we have big shoes to fill here. Nobel Prize in 1995 by Mario Molina when he was a faculty member here. At that time, someone else who's still a faculty member here, Ron Prinn, was already measuring the chemicals that produce ozone depletion. That was Mario's interest and Ron's interest and my interest, of course, a very important topic for the world. And what Ron has done is been with a consortium of people from all around the world, set up stations where they do surface measurements of gases. And among the gases that they measured was this one, methylchloroform. And this one tells a tremendous story of how humans can actually solve an environmental problem. An incredible history that Ron has had. And so what he's been able to show is the way that the Montreal Protocol, a UN agreement, and its subsequent amendments internationally actually worked to not only turn the corner on the rise of this ozone-depleting gas, but actually drive it down to essentially zero now. So humans have triumphed in this story. But we need to be cautious on other stories, and Ron's turned his tremendous skills to measuring greenhouse gases. This guy, SF6, is one of the most potent greenhouse gases there is because the sulfur-fluorine bond is a tremendous absorber of infrared radiation. Those sulfur-fluorine atoms, they're all dancing around out there, and there's 6 of them, so and it lives a long time. It has a lifetime of many hundreds, if not thousands of years, and it's being emitted in large part, actually, from transformers. So we have to make sure that when we go through this energy transition to increased wind power, that we do it with transformers that are tight and not leaky. And that's unfortunately not the case in Western China. You're seeing a doubling of SF6 emissions from that region, which is considerably more than was expected. We've increased our strength recently in pollution studies and in tropospheric chemistry with the addition of Arlene Fiore, the inaugural Stone professor. And one of the things that she studies is pollution, is smog. The New York City ozone smog formation on the worst days is now become very sensitive to what we do with atmospheric NOx, and she was able to show that with a remarkable contribution of a mix of both surface data and satellite data, and things like the ratio of formaldehyde to NO2, which is what she's showing there, the way that changes. And of course, another thing that's coming up for atmospheric chemistry and that a number of us are involved in is wildfire. It's becoming a tremendous problem exacerbated by climate change. And the things that are emitted include organic molecules, which are extremely reactive chemically. And I'm studying that actually in my group too. So let me just close by remembering, of course, the tremendous history of our department in atmospheric dynamics. And we, again, have very big shoes to fill in Ed Lorenz and Jewel Charney. But we have recently hired Talia Tamarin-Brodsky, who's doing tremendous things, I think, relating to heat waves and looking not only at what happens at the surface, but what happens at altitude and what sets the maximum temperature during extremes. And you'll hear much more about climate and heat waves this afternoon. I don't really have time to talk about David McGee's work, except to say that this is David on his hands and knees, sampling, I think, one of these archives of past climate, which he uses to determine things like changes in rainfall. They've told me I'm out of time, so let me just pass it over now. The skills that we have in atmospheric dynamics, Wanying Kang is a tremendous person who has joined excuse me, sorry about that, and is using that understanding of atmospheric dynamics on the Earth to look at things like icy moons like Enceladus. And I'll turn it over to Ben Weiss.
Excellent. Hi, everybody. Nice to see you all here. I'm Ben Weiss, for those of you who haven't met. And I'm going to talk to you about the present program in planetary science. Oops, that's not the right way to go. Big green button. So there are 15 of us right now. And since I got here, we range all the way from recently hired junior professors all the way up to emeritus professors. And I got here around 2004, and since then, like, this program has grown quite a bit. It's like more or less double in size since I got here. And that's largely because, not entirely, a lot of the hires that have been centered in other programs, the ones you've just heard about, have naturally cross-cut in their interests into planetary science. And that's really because of two different things. One, there's this increasing realization that the Earth is a planet, and we understand that from many different perspectives. You heard a lot about, for example, thinking about it from a climate perspective. And then the second thing is that the increasing discovery of planets is providing more and more venues for understanding the basic physical, chemical ocean, atmospheric, climate processes that you heard about that we see on the Earth. So it's the field of comparative planetology is a beautiful way to understand the Earth, for example. And of course, there's many other people in the group, there are many research scientists, postdocs, and students, and I'm going to choose three different themes that cross-cut the Planetary group to talk to you about. Like the other groups, we use a variety of different techniques to address these cross-cutting things. We do laboratory work, we do astronomical observations, we do spacecraft observations, we do theory. Let me go back. So we're going to talk about solar system formation, ocean worlds, and icy moons, and the search for extraterrestrial life and planetary habitability in general. So starting with solar system formation, those of you who haven't met Rich Teague is one of our new faculty members who's an astronomer, and he's been using this Atacama large millimeter, submillimeter array. And he's interested in the broad question, as is Nicole Nee, you see pictured up there in the upper right, in how do planets form? Rich is taking the angle of using this new high-resolution telescope that can actually directly image structures in protoplanetary disks. These are the birthplaces of planets throughout the universe, these two-dimensional distributions of gas and dust. You're probably well aware that there's been thousands of exoplanets that have been found over the last few years. But what some of you may not have heard of is that over the last few years, there's actually been direct detection of planets within protoplanetary disks. So these are actually planets that are in the process of forming. We can actually watch them form. There's some beautiful data by Rich showing this happening here. So you have this image of face-on image of a protoplanetary disk here. What you're seeing here is not how bright the disk is, but the velocity structure. And we've removed the average component associated with orbital velocity each radius. So you're looking at the residual velocity associated with departures from that typical orbital velocity at every radius, with red being counterclockwise and blue being clockwise directions. The stronger the color, the faster it's moving. What you see is this spiral structure here. And also what you see is this kind of transition from counterclockwise to clockwise rotation right here. Without going into the details, this is a dead ringer for a planet forming in that upper left quadrant. It's gravitationally interacting with the gas around it. And this is opening up a whole new area of understanding planets by how they form by watching it actually happen. I also had a great slide about Nicole Nee's work, who's studying meteorites at the basically materials of our own early solar system. I didn't have time to put it in here, but I encourage you to ask her about nucleosynthetic anomalies in moderately volatile elements. Got that? And she's actually got a fantastic new result from that, where she's discovered pre-solar material in meteorites. All right, so next slide. What about icy moons and ocean worlds? So this is work by Jack Wisdom. There's been two kind of mysteries about Saturn that have been largely unexplained. Why does it have such a large tilt? Why is the angle of its spin axis so high? It's about 27 degrees. You usually expect planets to form basically with their spin axis parallel to the plane of the solar system. And how did its rings form? They're apparently only 100 million years old, according to some people. Jack and his student Rollo, who some of you may have heard yesterday, think they can explain both observations by the presence of an ancient moon in Saturn's system, which they dubbed Chrysalis. The motion of this moon caused Saturn to gravitationally interact with Neptune, tilt Saturn on its side. At the same time, the motion of this moon led to a close approach with Saturn, and it got destroyed about 100 million years ago and made the ring. So you're looking at the remnants of that moon right there. Then there's a bunch of us working on different aspects of ocean worlds, from Jupiter ocean worlds on the left to Saturn ocean worlds in the middle to putative ocean worlds on the right. We're kind of asking two broad questions. Where are ocean worlds in the solar system? We care about that. And the second question we're asking is, what's the nature of the oceans for the worlds that we are confident they are present? How thick are the oceans? How thick are the ice? What's the composition of the water? These are really interesting questions because ocean worlds are natural laboratories for understanding the orbital evolution of moons around giant planets, like we just heard a second ago. They also may be the most common habitable environments in the solar system, and a lot of those parameters about the ocean will be critical in understanding that question of whether they are habitable or not. And we're using basically spacecraft images, spectroscopy, Wanyin Kang in the upper left there and John Marshall are doing dynamical studies where they actually can understand how oceans flow within these ocean worlds, and a bunch of us are using spacecraft magnetometry to search and characterize oceans around these moons. Okay, and finally, the search for extraterrestrial life. So today, Mars is cold and dry, and but images like this on the left of Jezero crater here have long indicated that Mars was once warm and wet. Apparently, water was flowing on the surface in these valley networks. In this case, this one apparently breached the crater rim and produced what looks like a delta, something like you see at the end of the Mississippi River, apparently filled this crater up with water. So there's lots of questions about this. When did it happen? How long were these flows? That question, and how much water was involved, that particular question is of great interest to Gaius Duckey, a new hire, who's been studying orbital observations of these crater lake chain systems, because it turns out this one breached the other side. Water actually filled all the way up like a bathtub, flowed out the other side of the crater, and then in some cases that happened over several different craters in a row, chained together by these valley networks. You can actually quantify the amount of water associated with runoff episodes by seeing which of these craters filled up and which will then never quite fill all the way up to the top to breach. From a totally different perspective, Tanya and I are involved in the Perseverance rover, which is exploring this crater, and we're acquiring samples. The idea is to bring these samples back, which will hopefully, answer all kinds of questions, beginning with how long was this lake present, which is a key question as to whether it was habitable, and then overarching all of the goals of this mission is to search for fossils of ancient Martian life. Okay, and so I'm going to end with one last thing. What about life throughout the galaxy? So, Julian, there's a big question is, can we actually find planets whose atmospheres we can characterize that we think might be habitable? So that's a hard thing if we're looking for Earth-sized planets and we want them to be temperate. It turns out the best such objects, ones that could be characterized with current telescopes, like the James Webb Telescope, are these so-called ultra-cool planets around ultra-cool dwarf stars. These are the most common stars in the universe. They make up 65% of all stars. They have unbelievable ages. They're likely to last up to trillions of years. I said that correctly. And they're the best targets for characterization with James Webb. We only know of a half dozen of these right now. And so one thing that Julian's doing with this search is to try to double that number, even triple it. Okay, so I'm just gonna end then. Without saying too much here, there's a lot of stuff that's going on. What about the next 20 years when someone else is standing up here and I'm in one of the emeritus pictures? There's so many different things this is just stuff that we're involved in from our own group, and I'm just gonna highlight the first two. We've got this Morningstar mission led by Sarah Seeger, the first private mission to another planet. It's gonna hopefully characterize any carbon cycle that might be present in the atmosphere of Venus. And then we've got the flyby of the first Trojan asteroid by Lucy with Rick Binzel in 2027. And then the list goes on. Thank you very much.
All right, thank you all. I feel like I understand EAPS better now. So I'll just invite you all up and we'll do a short Q&A. There are two runners, Dave and Madeline, who will be bringing the mic to you. So after I call on you, just wait for the mic to arrive. Questions for any of these four? Yes.
The silence is so intimidating. I have to have a question. So fun to hear from all of you. Those were great. My question is, what are you doing to bring the groups together to work on climate issues across MIT? That's always one of the big challenges here, is so much excellence and some siloing. And now I know there's so much climate stuff going on, and each of your groups is working on climate. Are there ways of bringing it together for bigger impact?
Oh, you don't have to turn it off. It's already out. Okay. I don't think it's on, actually.
This is to control it.
Okay. There we go. Yeah. There's a lot of things going on to integrate across the groups. One thing that maybe worth mentioning is that I think as the interest in geologic hydrogen perhaps progresses, we need to really be talking together and thinking about hydrogen's impact on the atmosphere, because its climate effect is not zero. So it's going to leak, just like methane leaks. And I think it's an opportunity, if we do move in that direction, to really think about what it takes to make the systems tight. That's what's going to be required if you're going to do that and protect the climate at the same time. People imagine hydrogen is perfectly green. It's not. So that's the sort of thing that, I mean, I could talk about why, but, you know, I think the timing lady would actually give me more signals. But I think that we have many, many opportunities of that type. The idea of enhanced weathering is in another interesting category, where how does that feed back to the carbon cycle, and what are the impacts on CO2? We also have work going on relating to biological, Andrew Babin's work on how particles, organic particles now, not the inorganic ones that I talked about that Ed Boyle studies, but organic particles sink in the ocean and take up carbon. How does that carbon eventually get down to the seafloor where it can mineralize and become a permanent sink? So all those things are in our grasp, and we are working across groups on them.
One more question, Ken. Oh, we have two questions here, Ken and then John.
You know, one thing that's come out of visiting committee is this whole issue of basic science versus applications or solutions, whatever. And that's always obviously a tension, but realistically money goes to solutions and goes to engineering rather than basic science most of the time. What is your appraisal of that situation now, and how do you feel about it?
Well, I can speak for Brent Minshew, who I'm not sure is in the room or not, but you know, he's looking at solutions for trying to essentially stop glaciers from moving. There's proposals out there to pump water out from underneath the glacier to stop it. And that's a solution to a problem, but we don't really understand the fundamentals of the science, so there's a strong interaction there. And Brent's working with private money to do this. It's foundation funding. It's something you don't get out of the US government, for example, which is an interesting problem.
Yeah, yeah. I also find that I think it's less problematic than we think. I think there should always be basic science here, but if you do the basic science and you address these questions, you know, to engineer lots of these solutions, you need to understand the basic science. And my feeling is, with dealing with donors and you know, other agencies, they do understand that, you know. And I think there's more understanding coming towards this, that the basic science is really what it's going to lead us to identify the most successful solutions, you know. And of course, we can make more experiments and try this and try that, but if we don't understand it, you know, it's not as likely to succeed.
I guess I just want to chime in that many solutions come with risks. And we can't continue to just have the attitude that we're not going to pay any attention to the risks until they bite us. The way that we understand risks is to understand the science behind them. I think that comes up every single time you look at any environmental problem. You know, whether it be the use of leaded gasoline, which nearly poisoned all of America's children with lead back in the day when we were using it. You know, science is what showed us that that wasn't a good solution to making engines more efficient. So every single time you look at an environmental issue, you've got to look at the risk side, which invariably brings you back to science.
Okay, the next question was to John Southard, and then we have one more in the front, and then we'll close for coffee.
Here's a question out of total ignorance. You mentioned the ultra-cool stars, and you mentioned 1 trillion years. Well, that's many times the age of the universe. How do they know that they could last 1 trillion years?
Yeah, clearly, is this active? Yeah, clearly we haven't actually observed any of that age, right? And the reason I mention that is because that makes them important objects in the when you think about the future history of the universe, okay? But that is largely inferred from stellar nucleosynthesis models, where we understand, how stars form elements in a very precise way from nuclear physics. And so you can actually model their lifetimes and understand that very well, even though it's not observed.
Okay, then one final question here.
I've been here since 1961. When I came, the green building was going up, and it upset the airflow. And if you remember, the windows started popping out. And now, fast forward to 2024, the weight on the layers, Earth's layers, have tremendously increased. This was almost a wasteland. Now there's almost towers everywhere, and MIT is responsible a lot for that. I'm wondering if there is any interest in studying what's happening underground to layers of earth, rock formations, and whatever, and whether we're at risk once again for having disturbed not the airflow, but what's underneath.
That is mine? Okay, so I think it's more geophysics, but we do have people that are interested what happens to the Earth underneath when the load on the surface changes. But it's usually not related to one building itself, But people have studied what, for example, if you have a huge mine and you extract material, how the Earth responds by uplift, or if ice sheets move back and forth, how the Earth responds to it. And that actually gives us a lot of information about the properties about the deeper Earth. So we try to take advantage of it. But the green building by itself, while it may have an impact on the immediate soil underneath us, especially because we have a lot of water from the Charles here, for the deeper layers, it's probably not influential, but for the soil, it is for sure, yes.
I think I'd also add that we now have the technology, we can measure this very successfully. So millimeter level motions of buildings, either through GNSS or through synthetic aperture radar techniques. And there's been measurements made of tunneling systems where they can actually see the observed deformation as they're tunneling. You can see the front of where the tunnel is. So we can observe it, and then with this good, decent modeling, we can understand what's going on the subsurface as well.
Great. So let's join in thanking our speakers once again.